Solve the inequality. Okay, so we have two rational expressions on either side of this inequality symbol. First thing you want to do is to set the two inequalities to the left-hand side and set them equal to 0 as a result. So we're going to move this guy over to the left, and we're going to end up having 4 over x minus 5 minus 3 over x plus 2 is equal to 0. Now we want to rewrite this as one rational expression with a common denominator, so let's go ahead and do that. The common denominator will simply be x minus 5 times x plus 2, right? And basically, to go from x minus 5 to x minus 5 times x plus 2, we had to multiply by x plus 2. So we'll do the same to the numerator. Then we'll have a minus 3, and then to go from x plus 2 to x minus 5 times x plus 2, we had to multiply by x minus 5, so we're going to do the same here as well to the numerator. And all of that will be equal to 0. Now, if we distribute on the top here, we'll end up having 4x, right, plus 8 minus 3x plus 15. And all of that will be over, again, that LCD of x minus 5, x plus 2. When you combine like terms on top, you end up with just x plus 23, right? Because 8 plus 15 is indeed 23. And on the denominator, you have x minus 5 and x plus 2 equals to 0. Now we want to take those and separate the numerator and the denominator and set them equal to 0 separately. So for example, I'm going to say x plus 23 equal to 0, and that'll give you x is equal to negative 23. And what this tells us is that that's a 0 for the function. Negative 23 is a 0 for the rational expression. All right, let's go ahead and look at the denominator then. These will give us the undefined points, right? So x minus 5 times x minus 2, or x plus 2, set equal to 0, ends up giving us two solutions, right? We have a product that's equal to 0, so we can separate them separately, set them equal to 0, and see what they give us, right? Well, the first one will give us that x is equal to 5, and the second one will give us that x is equal to negative 2. So remember, these are the places where the function is undefined, right? Okay, so let's draw a number line and place these values on the number line. Now, when we do this, we need to start with the one that's furthest to the left. That'll be negative 23. Then we're going to go to negative 2, and then positive 5. Now let's think about what we'd test. We need to test a number in this region, so let's try negative 25. That's a nice round number near negative 23. Something between negative 23 and negative 2, how about negative 3? So let's go ahead and test negative 3 here, and then we can test 0 in this region because 0 is between negative 2 and 5. And then we might test something like, I don't know, let's say 10, for example, a nice round number that's after 5. All right, let's test the negative 25 and see what you get. We'd end up having 4, and then negative 25 minus 5 in the denominator, and we want to ask if that's greater than 3 over negative 25 plus 2. All right, so if you do this, you end up with 4 over negative 30, and we're asking if that's greater than 3 over negative 23, right? 25 minus 2 is 23. Keep the negative sign. All right, so you might want to pull out a calculator if you're not sure which one of these is bigger than the other, right? We can't reduce them to a common denominator, so it's best maybe just to get decimals, right? If you divide 4 by 30, you're going to end up with the decimal minus 0.133, right? Repeating. And if you do the other one, 3 divided by 23, you're going to get minus 0.1304. So the one that's actually larger is the 1304. So it's not true that negative 0.133 is greater than negative 0.1304. That isn't true, right? Because these are negative numbers. So we're going to say this area is false. All right, how about the other area of the number line, the one following that? Let's test negative 3. To test negative 3, I'm just going to replace these negative 25s with negative 3 and see if it's still true. Well, we have 4 over negative 8 then, and that's going to be compared to 3 over negative 1, right? All right, well, this is much easier to test. 4 over negative 8 is negative 1/2, right? Because 4 goes into both of those numbers, into 4 one time, 8 two times. Is that greater than negative 3? it is greater than -3, right? That is true. So we're going to go ahead and shade this area and say that that part of the number line provides solutions for us. However, let's make sure we put in the proper symbols. We're going to use a rounded parenthesis for both of these, right? For one reason, -2 makes the rational expression undefined, so we don't want to use -2, but also we don't have an equal sign in the inequality here. It's just greater than, strictly greater than, so round parenthesis will work for both ends of that region. All right, let's test 0 then. So to test 0, we're just going to replace that -3 in what we just wrote and put 0 in. Okay, so we put 0 in and we basically get -4/5, which is basically -0.8. And that's compared to 3/2, which is 1.5, right? So of course, negative numbers are never larger than positive numbers, so this is false, right? So this number being negative cannot be larger than a positive 3/2, right? Okay, so we know that area is false. Let's check 10, the last one we have to check. So we'll put 10 where the 0 used to be. That's nice and easy. We can just pencil in a 1 in front of the 0. So 10 minus 5 is going to be 4/5 basically when you're done with that arithmetic. That's a positive 0.8 essentially. And this other one will be 3/12. So let's reduce this a little bit. This will be 0.8. How does that compare to 3/12? Well, 3 goes into itself once and goes into 12 4 times. That's 0.25. So 0.8 is indeed bigger than 0.25, so this is true as well. Remember, we can't include 5, so we're going to round the bracket. That goes up to infinity. So we have our solution set then. Okay, so our answer for this one ultimately is from -23 to -2, union from 5 to positive infinity. And again, use the round parentheses for the entire answer because we do not want to include any of these zeros or undefined values. All right, so let's go ahead and look at example B then. For example B, it's already basically isolated on the left-hand side. It's already written as a single fraction or rational expression. So we can set it equal to 0 and begin the process of setting the numerator and the denominator equal to 0. So let's go ahead and do that. 1 minus x to the third power times x plus 3 set equal to 0, and then we'll do the x cubed minus 8 set equal to 0. All right, so with the first one, we're going to end up having 1 minus x to the third power is equal to 0, and x plus 3 is equal to 0. They're set up separately because originally they were a product, and remember, if you have a product and it's equal to 0, you can separate them separately and set them equal to 0. Basically, this one is going to give us the answer what? That x is equal to 1, right? Basically, if you solve that one, it's x is equal to 1. If we want to show that in detail, we can say what? Take the third power and expand it to say it's 1 minus x times itself 3 times, right? And that must mean that 1 minus x is equal to 0, right? And then, of course, 1 minus x is simply the same as saying 1 is equal to x. And so there's your solution for the first one. For the other one, it's going to tell you that x is equal to -3, right? This piece here. And then lastly, we have this one that's going to involve some difference of cubes factoring. So the way we do this is we basically break it up into a binomial times a trinomial. And the pattern is simple. It's the root of the first guy. So what did you cube to get x cubed? You cubed x. What did you cube to get 8? You cubed the number 2. You keep the same sign as you started with, right? Then the first position here will be this guy squared, so that'll be x squared. The last position will be the square of the second thing, so that'll be plus 4, right? And then, of course, you do the product of these two terms, right? Using the opposite sign of what you started with. So if you had negative, you'll make it positive, and the product of 2 and x is 2x. Okay, from there, you'll separate these separately equal to 0, so x minus 2 is equal to 0. And this other piece is equal to 0. So I'm just going to remind you something that's important. The piece that comes from the sum and difference of cubes factoring that involves the trinomial, that is always prime, which means you cannot factor it, and it also only has imaginary roots, meaning that you're not going to be able to solve that and get real solutions. So we don't need to worry about that part of it. We can cross that out. So we have 3 numbers that we have to divide up the number line with. Keep in mind again that this one causes the function to be undefined or the rational expression to be undefined. Okay, so we'll divide up our number line at these 3 places. So the first one appears at -3. Then we'll have +1. and then we'll have 2. All right, so we'll test, say, -4 here on this side. Then we can test 0 here because 0 is between these two numbers. Then we might test, let's say, something like 1.5 or 3/2, in other words. And then we can test something simple like 3. Okay, so let's see what happens when we plug in -4. Now, the arithmetic is kind of tedious here, so I'm just going to do it for you and tell you what you get, because otherwise it's going to take a little bit of time that's not really well used here in the video. So let's go ahead and just plug in the numbers here off screen, and then I'll tell you the answers. When you plug in -4, you get the value 1.736, etc., which is not less than 0. So that's false. So we're going to put a false there, or basically exclude that answer. It's not part of the answers, right? Let's try if we see what happens if we test 0. 0 we can write out because it's so easy, right? It'll be 1 minus 0 cubes, or in other words, 1 cubed. Then it'll be 3 in the numerator, right? Because 0 plus 3 is just 3. And then finally, you'll have 0 minus 8 in the denominator, or just minus 8, right? And then, of course, when you evaluate that, you end up with -3/8, which is less than 0, so that makes this part of the number line indeed true, right? Rounded brackets here and rounded brackets here, right? All right, good. Let's take a look at 3/2 then. What happens if we plug in +3/2? Well, if we put 3/2 in the function, we actually get a number like 0.1216, etc., right? In other words, we get a number that's greater than 0, not less than 0. So since it's not less than 0, we say, okay, that's false. So we'll say that this region of the number line does not provide solutions to the inequality. And then lastly, let's test 3 in the function. If we test 3 in the function, we get the answer -2.526, etc., which is indeed less than 0. So that makes this part of the number line true, or in other words, this part of the number line contains solutions to the inequality. So we're going to round the bracket at 2, and then we're going to go all the way up to positive infinity. So if we transcribe our solution set, it'll basically be from -3 up until 1, rounded brackets on both of those, right? Then union, we're going to pick up at 2, and we're going to go all the way to positive infinity. And that's essentially the solution set for inequality B.